So in today's video, we'll look at some more areas between curves. Some of them will be a bit more challenging examples, starting with this first one here. So you can just follow along as I show you how this would be set up. We're not going to actually solve this one, just set it up. Well, notice though, the y-axis kind of acts as a dividing line, where left of the y-axis, we really just have one curve where there's area underneath it and between the x-axis. So we can set that part up by just doing a simple integral from -1 to 0, and we can do it in terms of x because we're going top to bottom, so it'll just be x plus 1 to the 1/5 dx. So that essentially took care of this whole area right there. But now in this other part, we would have to do the top curve minus the bottom curve. And if we tried to do that in terms of x, that x equals minus y squared plus 3y, that would be hard to get y by itself. So we're going to have to do this other section in terms of y. And when we work with y's, we always do right minus left. Now the problem with right minus left is that the y value of 1, basically it switches over. Up until that dotted green line there, the right-hand function is that x equals y or minus y squared plus 3y, and then the left-hand function is just the y-axis. But after that dotted green line, it's that same right-hand function, but the left-hand function is now the y equals x plus 1 to the 1/5. So we're going to have to do two separate sections here. And while we're at it, since we're doing it in terms of y, we're going to have to get the y equals x plus 1 to the 1/5 with x by itself. So we'll start out by raising both sides to the 5th. So we'll have y to the 5th equals x plus 1. So therefore, x is equal to y to the 5th minus 1. So we will first do this section here. And to represent that area, again, we're going to do it in terms of y. So we're going from a y value of 0 to a y value of 1. Our right-hand function is minus y squared plus 3y. And then we'll have dy. And we've just got that one part because the left-hand barrier is just the y-axis. And that's our natural barrier when we're doing it in terms of y's. And then we'll add on our area for this section. So we're going to again do it for y's. Now we don't know what this y value of this intersection point is. So let's just call it a comma b. Therefore, we are going from the y value of 1 to the y value of b. Okay, we don't know what that value b is. We could hypothetically figure it out, but for the purposes here, just to show you the setup, we're not going to get it. So we'll do our right-hand function of minus y squared plus 3y minus our left-hand function, which is that green one that we got x by itself. We'll make sure to put it in parentheses because the negative applies to all of it. And we'll have y to the 5th minus 1. And then our dy. So this had a couple things we had to watch out for, and therefore made it a bit of a challenging setup. All right, next one we will actually go through and solve the whole thing. So we want to compute the area between f of x and g of x, where f of x is minus sine x and g of x is -2 sine x. And we'll do that from 0 to pi. So we'll sketch each of them. Maybe we'll sketch f of x in red. So negative sine x should start at the origin and head down first. So that's our graph of negative sine x. G of x, maybe we'll sketch in green. -2 sine x is the same thing, just it goes down to -2. And then we want the area between those curves. Well, to do that, we do top minus bottom. So we're going to do integral. Our starting x value of our region is 0. Our ending x value of our region is pi. The top function there is the f of x, so that's minus sine x. And then minus our bottom function, which was minus 2 sine x, and then we're dx. So this minus a minus really becomes a plus. Antiderivative of negative sine x is cos x. Antiderivative of 2 sine x would be negative 2 cos x. And we're going to be evaluating from 0 to pi. And before evaluating, we can neaten that up a little and just make it negative cos x from 0 to pi. We'll sub in our pi, minus, we'll sub in our 0. And remember, you always have to evaluate trig functions. So there's our basic cos graph. So we've got minus, cos of pi is negative 1. That really became a plus. Cos of 0 is 1. So this gives us 1 plus 1, which is 2. So our area between those two curves is just 2. Okay, this is another one we're just going to discuss and talk about, and we're basically just going to talk about how you would find the region that's shaded there. Well, they call that curved part f of x. Let's call this slanted line g of x. We'll call this slanted line h of x. And we're going to assume that that is 1.5, where it's splitting. Basically, what we have to do is we have to do the area of two different regions, left of 1.5 and right of 1.5. So for the first one, we would go from 0 to 1.5, and we would do top minus bottom. So we would do whatever f of x's function is, minus whatever g of x's function is, and then we'd be dx. And then we'd have plus, and now we would do it from 1.5 to 3. And now our top minus bottom would be f of x's function minus h of x's function dx. Now, we obviously can't solve that without knowing the actual functions, but this is the general setup that we would have to do. All right, let's look at another one that we'll actually go through and calculate. So we're going to find the area of the triangle that has these three vertices. So you're going to have to sketch a little xy axis on your paper. And we have the points 0, 5, we've got 2, negative 2, and we've got 5, 1. So we'll plot each of those points. And just to make it easier to refer to them, on the screen here, I'm going to make each of the sides a different color, just so it'll be easier to talk about. Now, to be able to find the area in between those, or in other words, the area of the triangle, we're going to do it with calculus, so we're going to do area between curves. So we are going to need to know the equation of each of those. Well, the red and the blue will probably be the easiest, and then the green will be a little bit more challenging. The red and the blue because they're clearly going through a y-intercept already. So in our red graph, we have a y-intercept of 5, and our side, it goes down 4 over 5. So the red one will be y equals minus 4/5 x plus 5. Now our blue one also has a y-intercept of 5, but our slope, we're going down 7 over 2. So we'll have y equals minus 7/2 x plus 5. And for our last one, the green one, so the slope there is going up 3 over 3. So that's really a slope of 1. The y-intercept is going to be minus. So if you follow that slope of -1 backwards, that's going to put us down at -4. So y equals x minus 4 will be our third equation there. So we're going to have to kind of use a strategy like we did on that last one we set up, because we're going to have to split this at x equals 2. Because at x equals 2, it switches from being red on top, blue on bottom, to red on top, green on bottom. So we'll have to do 2 separate integrals. So our first integral we'll do from 0 to 2. And we're going to have our red function, our minus 4/5 x plus 5, minus our blue function, and we'll want to make sure we put that in parentheses, minus 7/2 x plus 5, and then dx. Okay, so that's our one part. Plus, and I'm going to go to the bottom, the line below, just because I don't have the room. We'll go from 2 to 5. And we'll now have our red function minus our green function. So the colors help you kind of see the setup there. So from 0 to 2, we're doing the red minus the blue, and from 2 to 5, we're doing the red minus the green. Well, we're just going to do some neatening up now. So we're really going to have minus 4/5 x plus 5. We'll have plus 7/2 x minus 5 dx. Then we'll have from 2 to 5, we'll have minus 4/5 x plus 5, minus x plus 4, and then dx again. Well, negative 4/5 is like saying negative 8/10. 7/2 is like saying 35/10. So put those together, and we're going to have 27/10 x. And then the 5 and minus 5 wipe each other out, so we'll just have dx. And we'll have negative 4/5 x minus another x. So that'll give us negative 9/5 x, because minus an x is minus 5/5 x. And then 5 plus 4 gives us 9, and we'll have dx. So we're now ready to take our antiderivative. We'll have 27 over 20 x squared. Because the exponent goes up to 2, we've got to multiply by a half out front or divide by 2, however you want to think of it. We'll evaluate that from 0 to 2. We'll have minus 9/10 x squared by the same purposes, or by the same principles. Exponent goes up 1, divide by 2, and then plus 9x. and that will be evaluated from 2 to 5. So we will have 27/20 times 2 squared minus 27/20 times 0 squared plus, we'll sub in our 5, so we'll have -9/10 times 5 squared plus 9 times 5 minus, it's got more than one part, make sure you put it in parentheses, so we'll have -9/10 times 2 squared plus 9 times 2. Close parentheses. So 2 squared is 4. Basically, the 4 wipes out with a 4 on the bottom, and that'll just give us 27/5. Well, 27/5 is really just 5.4. The next part wipes out because it's just 0. 5 squared will give you 25. 25 divided by 10 is 2.5. 2.5 times -9 is -22.5. 9 times 5 is 45. 2 squared is 4 times -9 is -36. Divided by 10 is -3.6, but then we're negating it with the minus out front, so plus 3.6. And then we'll have 18, but it's being negated, so we'll have -18. And then when we bring that all together in the end, we will have 13.5 for the area of our triangle. All right, so we're going to look at one more example in this video. So we're going to have these two functions, and we're going to find the area that is bounded between the curves. Now this is what that picture will look like. They cross once at 0, 0. And then they'll cross again when x is equal to approximately 1.18. Okay, so this is going to be the approximate area. Okay, so notice the question had said, find the approximate area of the region. Okay, and the reason it's going to be approximate is because that root, or that, not root, but intersection is not going to be exact. So we've got to consider which one is top and which one is bottom. So we're going to be going from 0 to 1.18. Our top function is the x over square root of x squared plus 1. Minus our bottom function, which is x to the 4th minus x, and then dx. So setup, not terribly crazy. Actually evaluating the integral, a little bit more challenging. So what we're going to do is we're going to split this basically into two separate integrals. Because to be able to do that x over square root of x squared plus 1, we're going to have to use substitution. The second part, we're not. So we're going to split this into 0 to 1.18. I'm going to rewrite that fraction as x and times x squared plus 1 to the minus 1/2. And here, I'm going to switch that to a plus, but then switch these signs. So really, we're going to have plus the integral from 0 to 1.18 of a minus x to the 4th plus x dx. And we're going to treat this as two separate integrals. And again, we're doing that because the one on the left, we're going to have to use substitution. So our inside part there is x squared plus 1, so we'll let u equal x squared plus 1. Our du then would be 2x dx. And I just noticed that I need a dx here if I'm doing two separate integrals. Well, this is where our main stuff is happening. That's going to be our u to the minus 1/2. So our leftover is x dx. We currently have 2x dx, so we've got to multiply both sides by 1/2. So we'll have a 1/2 du equals x dx. And we'll now be ready to do our substitution. So we'll have 0 to 1.18. We will have 1/2 u to the minus 1/2 du. And maybe let's go ahead, we'll go through and do this part of the integral, and we'll come back and do the easier part there afterwards. So if our exponent goes up 1, we'll have u to the positive 1/2. And then we'll have to divide by that new exponent out front. Well, a 1/2 divided by 1/2 is just 1. So we'll have u to the 1/2. And that'll be 0 to 1.18. But then we've got to replace u with what it originally was. So we've got x squared plus 1 to the 1/2. And we'll be evaluating from 0 to 1.18. And we'll just pause it there, and we'll come back to that once we do our integral of the other part. So that's the hard part. So here we'll have we're going to have our exponent go up 1, so x to the 5th. Out front, we'll have minus 1/5. And then we'll have plus 1/2 x to the 2nd. And that will be evaluated from 0 to 1.18. So we may carry this down some. Just so we don't have to scroll up and down. So we are going to have 1.18 squared plus 1 all to the 1/2 minus, when we sub in 0, the 0 squared is 0, so we'll just end up with 1 to the 1/2. Now here's a case where 0 doesn't wipe everything out. Okay, so you can't just assume that 0 wipes everything out. And then this was a plus in here that I forgot to carry down. We'll have plus a negative 1/5, 1.18 to the 5th, plus 1/2 times 1.18 to the 2nd, minus, start a parenthesis because there's multiple parts. Now these will both be 0. 0 to the 5th times negative 1/5 is 0. 0 to the 2nd times 1/2 is 0. So those parts will be 0. And if we were to punch this all in, we would get 0.7853869,526. And that would represent our approximate area between those two curves. Again, it's approximate because we use the calculator to find that intersection point of 1.18. That's it for this video. We'll see you next class.